Hello, my name is Eric Andrews, and I'm here with Brandon O'Brien and Jerry Johnson. And our group project was the mechanical wear tester for Los Alamos National Labs. Our group advisor was Eric Johnson.
The goal of this project is to design and fabricate a mechanical wear tester. The tester will be used to test surface characteristics of exotic materials down at Los Alamos, and it needs to interface with the existing vacuum chamber that they have. The mechanical wear tester needs to scratch the sample at a specified stroke amplitude and stroke rate. The stroke amplitude needs to be variable between 0 and 40 thousandths of an inch, and the stroke rate needs to be variable between 0 to 200 strokes per minute, with the capability to provide a single stroke to the sample. The wear tester will also need to provide up to a 5-pound force on the tip normal to the test plate. Amplitude, stroke rate, and the normal force applied to the test plate need to be measured and recorded by the wear tester with tolerances of plus or minus 10%.
The apparatus must have interchangeable sample tips. In order to hold vacuum, it must mount to a 2 3/4 inch Del Seal conflap port. It also needs to be controlled through a LabVIEW interface.
After making a few hand drawings, 5 subsystems were chosen to be evaluated further. These are the tip and the tip holder, the force actuation mechanism, the force measurement device, the stroke actuation mechanism, and the stroke measurement device.
Shown here is a solid model of our proposed design of the mechanical wear tester. The bottom portion here is the existing vacuum chamber down at Los Alamos, and here you can see a rough estimate of where the sample is going to be. Our stroke actuation is provided by this linear actuator mounted on top, and the actuator actuates in this direction and slides this plate, which is connected to this flange and also to the bellows. It actuates up and down in this direction.
Here the system is shown in its actuated mode. These bellows here are flexible and they can be actuated on a stroke length of around 2 inches. This allows us to get out of the center where the sample is placed onto the sample holder here. Here in actuation mode we bring the tip to the center of the sample. The sample is already existing on the chamber, and they are able to apply the normal force via a screw system that exists already. Here's our tip holder system. As you can see, there is a set screw which holds this small tip in, which is a simple geometry and easy to manufacture. The force from this force arm here then deflects this cantilever beam, which has strain gauges at the top of it. These strain gauges then measure the deflection and provide info on the force applied by the sample. The wires for the strain gauge will come out these feed throughs here, which already exist, and Los Alamos already has the flanges necessary to feed the wires through.
While the system is actuating, these 4 steel shafts keep everything in alignment. The linear bearings seen here help to reduce the friction while also keeping the plate and the flange aligned properly. During actuation, the linear actuator has an encoder which measures the displacement and also the stroke frequency, and that's output to the LabVIEW control that we are going to build next semester.
Looking into next semester, a couple redesign considerations that came up during the CDR were changing the geometry of the beam to decrease the tip deflection in order to keep the force normal to the sample plate, while optimizing strain output. Also, looking into changing how the cantilever beam is attached to the conflap flange in order to have interchangeable cantilever beams. The 2 critical portions to next semester are constructing the LabVIEW VI and building a prototype to run the tests.
Love is a burning thing, and it makes a fiery ring.